I think we are good. You can see me and the content along with it. Okay, so let's do one thing, right? So in the last session, we have talked about how we visualize matrices and how do we actually represent matrices in three forms. We have seen three different pictures: row picture, column picture, and matrix picture. In matrix picture, we have learned one method which is called as Gauss elimination method, Gauss elimination and back propagation method. And in that method, we have specifically talked about uh, how we can see given system of equations in matrix format, and after that how can we find the given like solution for the given system of equations. We have seen that. Now what we will do is that along with it we have talked about something about elimination matrix, and after that we have seen what is permutation matrix, and we have seen two laws, which is associative law and commutative law. These are the two things which we have seen. Now in this lecture, where like what we'll be focusing on is that first of all we'll see how we can visualize matrix multiplication. Okay, we have been doing matrix multiplication in the above case, but we will see how exactly matrix multiplication happens, and what are the ways of looking at it, right? How do we visualize matrix, how do we multiply matrix? There are actually four ways which we'll be talking about, 4 5 ways, which it is really important to know and understand the pros and cons associated with it. So like we did in last session, we seen three different pictures and we have seen the pros and cons, positives and negatives of that. Similarly, we'll see matrix multiplication and how this 4 5 different methodologies work, and after it we'll talk about inverse. This is the like complete uh, part one of this session. After that we will talk about matrix factorization. That will be the second part. If time permits, we'll also cover that in this session only. Okay, let us start now. The first concept of this class is matrix multiplication. Okay, so here, let me directly draw or tell you that what are the different ways we have. There are actually 4 to 5 ways of looking at matrix multiplication, and all this 4 to 5 like ways boils down to one method, which we'll see in few minutes. But the traditional method is, let's say, I have a matrix. I have a matrix A. I'm drawing a square bracket and I'll expand that square bracket. Okay. So let's say I have this matrix. Let me zoom out. Again, we don't have like board right now. I have ordered it, but bear with me for the moment. Okay. So I will copy and paste this and I will reverse this. Okay. Okay. Got it. So let's say this is our matrix. And let's name this matrix as matrix A. Okay, we have matrix A, and I will copy this entire thing, copy and paste, and I'm multiplying with another matrix. Let's say this matrix B. Okay, and when I'm doing matrix multiplication, okay, let me open my book here. I have book. This will be helpful for examples as well. Okay, okay. So I have two matrix A and B. We'll see examples later on, but let's focus on the concept. So this is our method one. This is our method one, and in method one we are seeing two given matrices, and this method, I'll tell the name of the method, but let's say we have two matrices, and I'm multiplying this and I'm getting another matrix. Let's say this matrix is uh, control Z. Okay, let's say this matrix is uh, C. Okay, so I have matrix A, I'm multiplying with matrix B, and what I'm getting is I'm getting another matrix which is C. Now, there might be n number of elements. Let's say this is m cross n and this is n cross p. So we will get a matrix of m cross p. Okay. I hope you are with me. Like if you're getting lost, you just tell me, right? You can unmute yourself. You guys can unmute or just give a like. Okay. Now, what I have told you just now is that I have a matrix A, I have a matrix B, and I'm getting matrix C. Now, what I'm interested in, let's say let us assume that there is a point, there is an element, and uh, let me take this, right? Okay, control C. Okay. So here I'm interested in this particular element. This particular element. Let's say this element as C of actually let me write it big letter C of small, okay, whatever, ij. Let's assume that this element is at position C of I comma j. Now I want you to observe this particular element, the element C of ij. Okay, C of ij. Like observe the given element. I have matrix A, I have matrix B, and I'm multiplying with matrix C. And let I am taking one point, and that one point, that one element is C of ij. Now, how can I get that matrix C of ij? That is my question. How can we get that matrix? Can I write? I want you to cross verify this thing, that C of I comma j is equals to rho of A, rho of A at I. I'm taking the row of ith element, like ith element of row in matrix A, and I'm doing a cross product of column of A, column of B at J. Can I write that? I want you to speak up, tell me, and this is going to be a two-way communication. So I want answers here. Can I write this? Okay. Like tell me, like I'm like waiting for response. Here, let's say like this is my ith row, okay, and this is my jth column. And to get the element at this particular thing, I'm writing that row of A at column ith column and column of J of B matrix. Okay. Okay, ठीक है. So here, if I have to write this, can I write this? Let's say A of I comma 1 cross B of 1 comma j plus A of, let me write it, A of I comma 2 cross B of 2 comma j plus, like this will go on till I get the element A of k comma 1 cross B of k comma j. Is it correct? So basically, if you see, like in school we have studied, I don't want to make this very boring because we have 5 more methods to go on. If you're like, okay, so in schools we have studied that like we are taking one row and multiplying with the all the elements, and we are like taking the positions, like first element at the first position multiplying with the first position of that particular column, second position in this row, second position of this column. Basically, I'm doing that, and I'm showing that methodology to you in the form of dot product. Okay, and can I write this? Can I write this as I think we will not have summation, but I'll write sum of I'm representing summation like this, like of A of it will go from A of I A of I comma k cross B of k comma j, and here k starts from 1 to n. Whatever the elements I have will go. So this is the one methodology of looking at matrix in the form of dot product. You take row column, you take row vector and column vector, multiply it both, and you will get the answer of a particular position of an element. This is one methodology. I hope we are clear. Okay, this is one methodology. I want you to okay, I want you to interact in between the sessions. This is not going good. You can speak up.
Keep going. If I have doubt, I'll ask you.
Okay. ठीक है, sure. So this is one methodology. And talking about the second methodology, right? Like this is very method 2 is looking in the way of column. So in method 1 we have seen how we can imagine matrix multiplication in the form of dot product. Okay. Now in method 2 we are seeing how we can see the matrix multiplication in the form of column picture. So let's say I'm taking the same thing. Okay, I'll copy the same thing here. Okay, I'll copy the same thing and I'll paste in here, right? Okay. Okay, I got the thing. Let me copy and paste this as well. This one. Copy and paste, bring it in here. Okay, I have let me remove this point and all. We don't need this all. Let me put it out, and because I don't have whiteboard, it is taking a bit longer, but it's all right. It's all right. Okay, and paste it here. I'm bringing this bracket here. Okay, and this is our A and this is our B. Okay, now column picture says that let's say you have matrix A and matrix B, right? It tells that the answer that you are getting, which is C, is the linear combination of the columns of B multiplied by C. What I mean by this? So here, like we have columns, right? We have columns, like let me write it here. Okay, let's say there is column 1, this is column 2, okay, this is column 2, column 3, column 4, column 5, like this. I have a number of columns in column B. The answer, the resultant of the given matrix will be the resultant will be like this, column 1, and this column 1 of the matrix C would be A cross column 1. Are you getting me? Let's say this is column 1 and this is column 2 and this is column 3, like this. Now what happens is that the resultant is basically you take the first column, multiply it with column like column 1 with A. That is your column 1 resultant, like resultant column 1. After it, similarly, if I'm writing here, let me write it here, the second column would be AC2, and the third column of this resultant would be AC3. So here what I'm taking is that I have complete matrix and I have the secondary matrix. In secondary matrix, what I'm taking is that I'm taking each column multiplying with the whole matrix. That will be the first column of the resultant matrix. I'm taking second column multiplying with the A, like which is like the matrix which is given. So I'm taking the second column in B, multiplying it there, and that will give me the second column of the resultant matrix. So this picture is known as column picture. Similarly, there is another like alternate picture, which is row picture as well. In row picture, in method 3, what we do is that, let me write it capital. Okay, method 3 we see at the form of column picture, row picture, sorry, row picture. In this, what we will do is that, let me copy the same thing. Okay, I'll copy these things here. Copy and paste. Okay, I got this things here. Okay, this bracket is missing. Copy and paste and take it here. Okay, I have let me draw a line Let me draw a different color line such that this shows that these two are two different concepts. Okay, so here I have column like my matrix 1. Okay, so let me draw it A, not A, 1. Okay, 1. This is my column, sorry, matrix A. This is my matrix B, and I'm getting answer C. Okay, now let me just delete it. So in column picture, what we do is that we see the resultant matrix as the linear combination of rows multiplied with column B. So here we take the row, we take the first row of column A, multiply it with B, and this will give the first column, first row of the resultant matrix. So let me write it here. The row 1 cross B will be the resultant of the first row of C. Are you getting me? Right here, if I'm writing like this thing, like let me remove this. If I'm writing the second line, this is the second row, right? So we take second row, multiply it with the old matrix, and you will get the answer, which is the second row of the resultant matrix. This will give me R2 of B, row 2 cross B. So this is the row picture, which is totally sort of opposite to the column picture multiplication, right? And all this will give you the same answer. Okay, now the third way of looking, the fourth way of looking at matrix multiplication is, let me take black ink again. Okay, the fourth way of looking is row cross column. Oh, sorry, column cross row. Okay, so in column cross row, what we do is that I have examples here. Let's say we'll talk about examples in a while, but let me paste it again. Okay, let's copy this thing. 1, 2, 3, 4, 5, 6, 7, 8, oh god. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Copy and paste it. We really need a whiteboard here in order to fasten the lectures, or else it will be like this. I can't explain properly. Okay, so in this, what it tells us is that take first column. Let's say we have first column here. First column is column 1, and second column is column 2, and third column is column 3. Okay, let's assume that we have 3 columns and we have 3 rows as well. I'm just taking an example. Okay, it can be n number of rows, it can be n number of columns, any like number of columns and rows can be there. But here, let's say this is my row 1. Okay, row 1. Similarly, row 2. I'm just drawing things here. Okay, row 2 and row 3. Okay, row 1, row 2, row 3. Now the resultant tells that the resultant matrix C will be equals to column 1 cross row 1 plus column 2 cross row 2 plus column 3 cross row 3. So whatever the columns you have, take all those columns, multiply this corresponding matrices, corresponding rows, and you will get the answer. The sum of all this rows multiplied to its corresponding columns, whatever multiplication it gives you, sum them up and you will get the resultant matrix. This is the fourth picture. This is how we look at the columns, and this method, this fourth method and this second method are going to be really important when it comes to machine learning, when it comes to how computer solves problems, because computers solve problems through this perspective only. To be specific, if you see LLM architecture, let me just show you, like I don't want to make this session very boring, so let me take you to a different scenario, right? So LLM architecture and nano, I think there's a like overview, right? Let me see. There's a website. Yep, I think this one only. So here you will see like this website is responsible to see how LLM architecture works. And if you see Nano GPT, right? Nano GPT is the oldest model of GPT, right? This is how the architecture of Nano GPT looks like. And what happens is that whenever computation happens, this Nano GPT or any LLM model, GPT-2 is there, GPT-X is there, GPT-3. Right now, the model which we are using is GPT-5. So this is GPT-3. All these are transformers which are attached. Thousands of millions of transformers are attached together in order to like complete that compute. Okay, this is totally different topic. This we are going off the rails, but I just wanted to show you here that uh, whenever computation happens, like wherever computation is needed, let's say you are giving two matrices and telling your GPT to solve the multiplication, you know which one it will choose. It will choose this second picture. The second picture will be there. Internally, this is how the LLMs does all the operations. Okay, and as humans we follow this approach, and basically all this will give you the same answer. And basically if you observe very clearly, we are talking the same thing, but we are looking at the perspective, like the perspective of solving is different. Like here we are doing cross, like dot product. Okay, and here we are taking columns. In this thing we are taking rows, and in this thing we are taking rows and columns, sorry, columns and rows. Okay, and there is another method, which is fifth method, seeing matrices as matrix as blocks. Okay, and this is this method particularly is useful for large matrices. When you have 11 dimensions, 12 dimensional matrix, then internally your system breaks that large dimension matrix to smaller dimension, find the product, find the like multiplication of those smaller dimensions, and then combine it to get the bigger dimension picture, right? Bigger dimension answer, right? So let me show you how this work as well. Let me paste it. Okay, I have this thing here. Now what we do in matrix as blocks is that we break our matrix in different pieces. Okay, so I'm breaking my given matrix A, okay, in 4 pieces. Similarly, I'll break the matrix B in n number of pieces. Here I'm breaking in 2 pieces. Okay, so when I put this 2 lines, I'm getting 4 different segments. Okay, now just assume that this particular thing, okay, let me write it here, A11 with small representation A1. Okay, here A2, this is A3, and this is A4. I know this session is going like a little bit boring, but believe me, this is a bit slow. But once we get in inverses, it's gonna be really interesting. So bear with me for a few minutes. After that, it'll be really, really interesting. Okay, so tell me the first column, like first of this particular element. If I break this C into the same like lines, then let me write it. Let me, okay, line. Okay, if I have to break the same thing, then tell me which one is it. I'll put line here, like which segment, how you can represent different segments. So can I represent this particular segment as A1 B1 plus A2 B3, and this segment as A1 B2 plus A2 B4, because this is B4, not 4-1, right? Like this, we take a matrix. Let's say, imagine that this is a very big matrix. So what we do is that you partition the given matrix, you consider this as a small matrix, you find the product of that small matrix with the rest of the matrix, right? And whatever the product you get, you put it here. Similarly, you find the product of this segment with the rest of the matrix, you put it here. Similarly, you find the product of this small block with the rest of the matrix, you put it here, and find the small block of the given matrix and put it here. And what you will get? You will get a resultant matrix. This is how we see. These are the 5 different pictures of looking at matrix. Very boring stuff, I know, but we have successfully completed how to see matrix and what are the different ways of looking at matrix multiplication. Now, tell me which method do we use? We use this method and this method. That's it. We don't see all these methods, but when matrix was invented, when mathematicians first started talking about matrices, this is the first approach we thought of. And this will work, all this will work, but this is the most mathematical description of the given two matrices multiplication. Okay, so I hope you got the point of how we see matrices. Now let's talk about the inverse of the given matrix. Inverse, second topic, inverse. Okay, inverse of a matrix. Let me zoom it, or else let me make this thing a little bit bigger. Okay, let me make it bigger. Okay, inverse of a given matrix. Inverse of a given matrix, and here I'm writing square matrix. Okay, now I want this session to be really interactive. I don't want any sort of like people sleeping in my lectures. I don't want that ever to happen, because max is the best thing and most interesting thing actually if you pay interest. Okay, now what is the inverse of a matrix? That is the question we need to answer first. After understanding inverse, we will see how to find inverse, but let's talk about inverse. First of all, how can I explain the meaning of inverse? There are two ways of explaining it. One is mathematical description. I can write a equation here and tell you that if this condition is satisfied, then the given matrix is a inverse matrix. Okay, then the resultant is the inverse. There is an inverse, right? Through properties, through mathematical stuff, I can explain you. And sorry, there is another way of looking at this, which is the essence, the fragrance of inverse, right? You have to smell it, you have to feel it when I talk about inverses. Okay, so here I'll tell the both ways. First, let's go into the mathematical description. Okay, the mathematical description says that if there is a matrix A, right, and if the given matrix A is a good matrix, I'll tell you what is a good matrix or a bad matrix, right? In previous first lecture, we have talked about what are good equations, what are bad equations. Similarly, what are equations? What is a matrix basically? A matrix is a representation of the given equation, right? If we are talking about linear algebra, like, as I told you before, the foundation of linear algebra is built. The matrices are built to find solutions of system of equations. So, can I tell that if the equation is good, it means that it has solutions. If the equation is bad, it means that it doesn't have equations. Similarly, when I'm saying that if the matrix is good, then it is a non-singular matrix. What is non-singular? Okay, how can I tell? Okay, uh, I want you guys to imagine that we have a matrix, right? Let us assume that it is a square matrix, 3 cross 3 matrix. When I say 3 cross 3, there are 3 elements. In column, there are 3 elements. In a given row, there are 3 elements. Okay, and there are 3 columns, there are 3 rows. And if you take one vector, if you consider one column as a vector, then the given column, right? When I'm saying non-singular, the given column is not parallel with the rest of the vectors. If you take any vector out of the matrix, the given vector should not have any correlation with the rest of the vectors. If it is parallel, if they have some sort of relation, right? If both are aligning together, or both are equal, or both are parallel, if you are taking these conditions, then it gives us a condition called as singularity. Okay, and what happens at singularity? I'll tell you what happens at singularity, but singularity is the worst condition. And for the matrices which are singular in nature, they won't have inverses. I'll talk about like exactly like when a vector does not have inverses and when a vector will have inverses. But mathematical description says that if a given matrix A is non-singular, then there will be a matrix, let's say, that is A inverse. Okay, let me write how I'm supposed to write A inverse. Okay, let me draw it on top. Okay, A inverse. Okay, here let me put this little up. Okay, so there exists another matrix which is I'm representing is as A inverse. I'll talk about what is this A inverse and how we'll find it and all. But when you do a multiplication of these two, it will give you identity matrix. And there's another thing like A inverse. Let me copy these two things. Okay, copy and paste. Okay, let me take it here. I know I'm confusing you guys, but this is really, really important as well. If you remember, okay, let me go up, little up, little up. I just wrote a law that A B is not equals to B A. But here I'm writing A cross A inverse is equals to I, and it is equals to A inverse A. So let me write it. Let me remove this thing, and I'm writing A, and I'm taking this inverse here. I hope you're getting what I'm trying to tell. Even though the order is changing, I'm getting the same identity matrix. Whether you take A inverse A, it will give you I. Whether you take A inverse, it will give you I. It is a very strange property actually. And to prove that how this is exactly possible, it's a tough thing. It's a really, really tough thing to prove this equation. But mathematically, if you observe, let's say you have a matrix A and you're multiplying with matrix X, and when you are multiplying the given matrix A with some matrix and it is giving you I, then in that case that X matrix is the inverse of the given matrix. That is the mathematical definition of this inverse. Okay, got it? Now let's talk about the essence, the fragrance, the meaning of inverse. Okay, so let's take this thing. I have matrix A and I'm doing some operation. Okay, I'm doing some operation. Let's say this operation is x1. After that, again I'm doing some operation on the same matrix. Let's say operation x2, and after that again I'm doing an operation x3. Okay, after doing this n number of operations, again I'm getting, let's say I got some resultant x. Okay, let's not say x, let's say resultant r. I got resultant r, right? So I have a did something on A first, after that again did something, after that again did something, and as a result I got R. Okay, and I want you to really, really hear this what I'm saying. In this process, when I'm doing different operations, x1, x2, x3, actually not x2, x3. Okay, when I'm doing different operations, I might add, I might subtract, I might multiply. And I want you to tell me this, that when I add, will the dimensions change? Let's say I have a matrix, I'm adding it with some constant or some another matrix. It can be anything. Will the dimension change? Mostly 99%. I don't know 1%, but mostly it won't change. Now let's say in x2, I'm doing some subtraction. It won't change. Mostly it won't change. But let us assume that in x3, I'm doing uh, I'm doing some multiplication, and when I'm doing multiplication, dimension changed. Just imagine that you had a square matrix and you did something on that, and what happened is a 2 cross 2 matrix reduced its dimension to 1 cross 1 or a single element by multiplying, by removing, by doing something. You have changed the dimensions of the matrix. Okay, now you want to go back You have reduced, let's say you are in three-dimensional space and somehow you did some operations, and because you did operations on the given matrix, somehow you are able to transit the dimensions of the given space, right? From 3D you came all the way to 1D or two-dimensional space. Now you want to go back to this particular three-dimensional space where you came from. To go back, what you do is that this going back operations is nothing but A inverse. This is the meaning. This is the meaning of an inverse. So when you perform operations, right? Well, let's say you're performing a line of operations. The reverse of that line is the inverse of A. Basically, A is the opposite of A inverse, and A inverse is the opposite of A. Okay, so if you multiply R with A inverse, you will immediately get A. And if you multiply A with R, you will immediately get A inverse. Are you getting me? So these two are the mirrors of two opposite spectrum, two opposite sides. Okay, so if you are going in this path, if you are doing this like dimensionality reduction and you reached one path and you want to come back to the previous path, then you have to do the inverse multiplication with the resultant and you will go immediately go back to that space. Okay, got it. Got it. Now let's not do like a lot more theory, because for the 20-30 minutes we have been talking about theory. We haven't taken any example. So I just want to show you that I hope you have understood the mathematical definition of inverse and how do we actually imagine inverse. Okay, and for newbies, for the people who are hearing this stuff for the very first time, I hope like most of professors don't tell these things in detail, right? So you might be hearing this for the first time, but when you hear this for the first time, I know it is hard to digest, so I want you guys to go ahead and search it, right? And I'll provide you the book right now, right after the session in the group chat. You can read it out, the book. But yeah, this is how we see inverse. This is how we like define the meaning of inverse. Okay, now how can we find the inverse? Okay, Jabir, uh, and we have talked about the definition, and this definition is the good part, right? If inverse exists, right? If inverse exists, then I have told you what is inverse and all that. But what if inverse doesn't exist, or how can you tell that for the given matrix there is no inverse? How can you tell that, right? Let's talk about the bad condition as well. What is bad condition? Bad condition. Okay, now let's say I have a matrix A. Okay, and that matrix is, let's say, 1 2 and 3 6. Okay, this is my matrix. Okay, now tell me that how can I tell that my given matrix is a bad matrix? When I say bad matrix, it does not have a inverse. We can tell by determinant. But have I teach you determinant? No, I haven't teach you determinant, so we'll not go there. You can calculate determinant. When you calculate the determinant of this given matrix, uh, you will get 0. Tell me, like, first of all, calculate determinant and tell me whether, sorry, you are getting 0 or not. Go ahead and tell me, I'm waiting. I hope we should get determinant. Okay.
Yeah.
No, is it, are we getting determinant 0 or not? Okay, whatever. So I like when you calculate determinant, you will get to know that by the conditions of determinant that the given matrix is a non-invertible matrix. It means that you will not have any inverse of the given matrix. Okay, and right now my question is, did we study about determinant? We did not study about determinant, right? So how can you tell, if you don't know the concept of determinant, how can you tell that the given matrix is invertible or not? There's a very simple thing, that if I'm writing, if the matrix satisfies, if any given matrix, right, satisfies this thing, that A, which is the matrix, multiplied by vector x, if this is giving me 0, then the given matrix is a non-invertible matrix. It doesn't have inverse. I hope you have understood what I wrote. So like, let's see the column picture of this particular thing, right? Take first column 1 3, take second column 2 6. Okay, now imagine the picture, right? Imagine the uh, I can draw, I can, like, I'm not gonna do that, because we have a problem statement to see how we can see, like, we have to complete one more you can say, like, point here, one more module. But the thing is, when you draw the column picture, the vector of column 1 and column 2, you will see that both are parallel or both are same. Basically you are multiplying with column 1 two times, like, if you multiply column 1 two times, then you will get column 2. It means that both are same vectors. Because both are same vectors, we won't have a it is a singular matrix, and we can't find uh, the solution, the inverse of the given matrix, if the matrix is singular. So tell me, right, I have a matrix, right, 1 2, let me draw here 1 with black ink, of course, the okay, 1 2 1 2 and 3 6. Okay, so if this is the matrix, and I'm gonna multiply this matrix with another matrix, let's say this matrix has x. Okay, so let's say this particular matrix has x. Okay, let me draw x properly. Okay, now how can I get x? This is my question. Tell me, what is this x? Tell me the value of x. Tell me, what is this vector? Find out. Can I write the answer as 3 and minus 1? See, if I'm multiplying the matrix A with x, which is 3 minus 1, then I'll get answer 0, 0. Is it or not? Well, you guys can give me thumbs up or anything. Is it or is it not?
It doesn't give 0, I think.
You have to multiply it properly. It does give 0. It does give 0. You just have to multiply it. You can take a screenshot, give it to GPT, and GPT will give you the answer, right? Uh, and if you don't find 0, it means that you don't know how to multiply matrices. Simple answer. Okay, now moving forward, so we got this thing. uh, this is the thing I want you guys to remember, that if you, how can you tell a given matrix is whether it has inverse or not? if it does follow this condition, if you're taking that matrix and multiplying with some x and it is giving you 0, if you're getting valid numbers, it means that it does not have inverse. You're just wasting time in finding inverse. It will not have inverse. Okay, by this thing you can tell that whether matrix have inverse or not. Okay, now how can we find? Let's talk about how to find inverse. Okay, then we will talk about mathematical description as well. Okay, now let's say I have a given matrix 1. uh Wait one second. Wait. I think this has to be 3 and this has to be 2. Okay, and this has to be 3. My bad. I thought I write 3 here. Okay, now you will definitely get a 0. I basically like interchange the numbers. You'll see, like, see now you will get 0 as a resultant. Okay, now here's the thing, right? How can we tell we have a number which is like determinant 0 or not? So let's say I'm taking 1 3 and 2 7, simple, right? A 2 by 2 matrix, because inverse is possible only for square matrices, right? I'll tell you why it is not possible for rectangular matrices after covering this entire thing. But yeah, let's say I have a simple 2 cross 2 matrix. Okay, now uh, how to find determinant? That is my question. What I know that I know that take it here. Okay, I know that here. Let me write it. A inverse, right? I'm taking A inverse will give me I. What did I study till now? I studied about this, and what I do to find unknowns. Let's say this matrix, X matrix. I don't know this X matrix. I take the augmentation. Let's try the same thing here. Okay, I'm just decoding things. So I have this matrix and I'll take the augmentation as well. Okay, and here I have 1 0, which is identity, right? So here let me just draw it. 1 0 and 0 1. Let me copy and put it here. So I have this matrix now. Now the goal is that in matrix multiplication, what we do, we have this matrix, we keep on doing row operations till we get upper triangular matrix. So I will continue my row operations now. Okay, what I will do is that, and the thing is, I keep on doing row operations till I get identity here. Okay, so what I'll do right now is I'll take row 2, and the goal is identity. So I'll take row 2 minus, I'll do row 2 minus 2 row 1, such that the beneath element will become 0. So if I do that, then what will happen? 1 3 and 0, and 3 7 minus 2 into 3, it will give me 1. Okay, now again I have my augmented here as well, and the same thing happens here as well. So the upper matrix will be same, upper row will be same, 1 0, and the low elements will be minus 2 and 1. Till here I hope I'm now clear. Now I'll do another operation. What operation I'll do? Let's say on row 1, the goal is to make this part as identity. So I'll take row 1 and do row 1 minus 3 row 2. 3 row 2. If I do that, then what will happen? Here the
Minus
element
2 minus 1.
here minus 2 minus 1. How is it? How is it? Here minus 2 minus 1. A 0 minus 1.
Yeah.
How? Where minus 1?
1 minus, nothing, nothing.
Okay. Okay, moving on. Um, so 1 minus 3 into 0 will be 1, and this will give me 0, and here 0 and 1. And what will happen here on the augmented side? In the augmented side, um, I will have 1 minus 3 into minus 2, which will be 6 plus 1, 7. And this will give me minus 3, okay, and here minus 2 and 1. Okay, now here I got the identity here. Okay, what is this? This is my identity. And what is this matrix? This matrix is nothing but inverse of A. And we call this entire method as Gauss-Jordan method. Okay, so to find inverse of a given matrix, we use a method, and the name of the method is Gauss-Jordan method. So this is how we find the matrix inverse, and this is the condition of telling whether the matrix has inverse or not. Okay, so I hope we are clear that how do we find the inverse of the given matrix and what happened here. Now like methodology is complete, like algorithm is complete. Like this is the algorithm. You perform row operation and you keep on doing row operations till you get I on the left hand, and whatever the element or matrix left you got on the right hand, that will be your inverse of the given matrix. Now if you multiply this matrix with this one, you will get I. Okay, clear. Now let's talk about some mathematics here, some mathematical description. Let's go back here, and then after talking about mathematical description, we'll stop. Okay, so I have A, right? And I'm performing operations on it, right? And can I write this thing? Can I write I'm performing operation on row 2 using row 1? So can I call that? If you remember, we studied elimination matrices, and I'm going back to elimination matrices because we mathematician represents everything with elimination matrices. Most of the times we don't do these operations at all. We just write E to 1. This shows that we are eliminating the elements in row 2 using row 1. Okay, and after that I'm again doing another elimination E1 2, and what I'm getting? I'm getting I. Okay, ठीक है, got it. So we got the thing. Now what can I write? I just want to give name to these two things. Okay, let me give a name. Okay, let's say the name I'm giving as capital E. Okay, now when I'm giving capital E, when I'm multiplying capital E with A, I'm getting I. Now let's go back to the definition. This is the definition. So if I'm doing eliminations, and after doing eliminations, my uh, equation is getting satisfied, then what is E? E must be a inverse matrix. E must be the inverse of A. Like basically we are just talking the mathematical terminologies of like we are just doing operations and observing that okay, what e must be the inverse of a. That's it, right? And when you send e there, you will get a is equals to I slash a inverse. Or basically yeah, this is the thing. I can remove this. This is the overall mathematical description of Gauss-Jordan elimination. So all these things I did that can be confined into this thing. So this is Gauss-Jordan method to find inverse of matrix. So I hope you have understood whatever the things which we have studied in this class, right? And the next class is going to be on, like, first we'll study few concepts, few laws, and then we'll talk about factor elimination, row spaces, column spaces, and all that, right? And most probably we'll do class tomorrow only. Tomorrow morning we'll sit and complete.